I would like to welcome everyone to today's talk, IM talk. I'm Azhar. I'll be moderating for today. I'm not sure if everyone can see me. I think there's a problem with my webcam for now. Okay. So I would like to welcome all participants and also the speakers for today's talk. And on behalf of IEM and also the Urban Engineering Development Special Interest Group, we are very happy for those that are willing to have the time to spend time with us to share some of our knowledge by our distinguished speaker today. Okay, so the topic of the talk today is on the urban flash flooding and revised curve number models. Yes. So I will introduce our speaker today. So the speaker is Engineer Associate Professor Dr. Ling Lloyd, and he's also part of our Urban Engineering Development Special Interest Group as well. And he's with BIODATA on him. So Engineer Dr. Lloyd Ling is an Associate Professor and a Deputy Dean of R&D and Postgraduate Program at the Lee Chian Faculty of Engineering and Sciences, LKC FES at the Universiti Tunku Abdul Rahman, UTAR. Is an Associate Fellow of the ASEAN Academy of Engineering and Technology, AAET, and appointed as a panel member of the Engineering Technology Accreditation Council, ETAC, and Engineering Accreditation Council, EAC, while he serves the Earthquake Technical Committee of the Department of Standards Malaysia under the Ministry of International Trade and Industry, MITI. He has been an active principal researcher and research member of national and several industrial research grants. Okay, so that was a brief introduction of Engineer Dr. Ling Lloyd. Without further ado, I would like to welcome Engineer Dr. Ling Lloyd for the to give his talk. But before that, if you have any questions, please put in the question box. We will address the questions after the talk. But if you can put it earlier, but we will address it after the talk. Okay. So proceed, Engineer Dr. Ling.
Thank you, Azhar, for the introduction. Can you see my screen and hear me okay?
Yes, I can see your screen.
Okay.
You can make it full screen?
PowerPoint slide. Sure.
PowerPoint slide. If possible. If cannot, then we'll
sure, I can do that. Okay. Let me turn off my webcam so to optimize the internet speed while I make the presentation. Welcome everybody to this research outcome sharing of mine supported by the Ministry of Higher Education through the FRGS, known as the Fundamental Research Grant Scheme. And there are few of the breakthrough outcomes that I would like to report today. Thanks for the Urban Engineering Development Special Interest Group, UED-SIG's invitations that I'm able to share some of my input and research outcomes on the urban flash flooding issues, along with the revised curve number model. Now, a lot of you actually may not be quite familiar with the curve number model, but if you're using any of the HEC, HED-RAS, HED-HMS products, HED-GeoRAS products, you probably will be dealing with the curve number, knowing or without knowingly. It's developed by the American and first introduced in 1954. And then I have the honor to work with a US professor, Professor Hawkins. And then we have been addressing and solving some of the issue as we go. Allow me to share some of the research outcome. Issues and photos like this, I think it's no longer new to those who stay in Malaysia. As you can see, Twin Tower is in the background as one of the photos. Even the Selangor and the KL area is not totally immune from it. You see the highway, and then there's a car traffic jam issue, basically being deterred by the flash flooding. And then you also see some of the vehicle being submerged on the upper right-hand corner. And caught a lot of us by surprise when during the off hour you try to be on the way back, and suddenly there's a heavy downpour, and then there's urban flash flooding. And then we also have the photos of those who have to seek refuge on the top of the roof, waiting for the NAPMA to come and basically pick them up. So these issues come and go. It just never really go away. A lot of people saying that the TID or the Majlis Perbandaran, the city council, is responsible for it. We try gotong royong or the community cleanup things, and then we also try to assess a lot of the urban drainage capacities. And at the meantime, NARIM, previously known as the National Hydraulic Research Institute, Malaysians working with GPS, they have been also involved in the research of the climate change, and one of the model they have been using is actually the curve number. So I wanted to share some of my video collection that I just pull up. On the left-hand side, you see like mini tsunami wave pounding on the shop lots and in the vehicles. All these cars, you know, that at this time that you will start wondering that how light they are, basically floating, you know, as the drive-bys, lorry or the bigger trucks hit them with it. This is the one of a collection that I used to teach my water resource class. And I look at the timestamp on it. It was December 2021. And here we in 2023, we're dealing with these issues again. I'm currently out of a state in Johor for a consultancy project and the field work. And the other day, now switching to the right-hand side, that we were tracing and we were doing some of the measurement in the nearby urban community. And then one of the student workers just keep on reporting at one of the location a huge surge amount of the runoff. And then to my surprise, I was actually quite lucky. I was driving around it and then I located the source of it. So you can see on the middle of the right-hand corner over here, there's a bursted pipes from the SHA things. So even during the sunny, hot days, that you will have incident like this, other than the rainfall amount pouring into our drainage. Try to imagine that if this unfortunate main pipe bursting issues happened during the heavy downpour or during the monsoon raining season, your drainage capacities basically will be out of capacities again. So with this kind of the issues ongoing things, the questions for my fundamental research is there a solution, or can we really actually get out of it? Now, the Professor Richard Hawkins that I mentioned about, he's with the University of Arizona in the USA. He was the first one to challenge the curve number theory. Those of you, if you're not familiar with the hydrology, if you pick up any of the hydrology textbook, there will be one full chapters basically talking and then about the curve number, elaborating about its extended use. It was taught in the university government agents throughout the world. A lot of university students basically just have to go through the hydrology class before they go to hydraulic by studying the curve number. And Professor Hawkins and I were talking way back in the 2013 and then 14. And then the concern that he raised was that as the ASCE senior fellow himself, that what happened that we are teaching our next generation of engineers the wrong thing over and over again. Even that thing was introduced by the US hydrologist or US geologist back in 1954. He found out that it really didn't apply that well in the United States of America. So I started working with him since at the end of the 2013. So you can see that to 2014 to 2017, the collaboration that I have with Professor Richard Hawkins was actually to search for the new methods of the curve number derivation with the inferential statistics. This was done under his recommendation after he fully exhausted the ASCE funding, American Society of Civil Engineers, grant him a research fund. So he conducted the field study, which later on I have a slide about that, going by state, try to verify that what was the curve number, indeed using the handbook, how far was it off and everything else, until that he exhausted the fund. So when he had his first discussion with me, they told me that in order to narrow the research gap, if it is possible to come out with the model calibration, or if there's a possible way, instead of using curve number or choosing curve number as an input, if you can derive the curve number, and then with the support of any of the applied statistics, that would be a breakthrough or to try to narrow the research gap. So I devoted a few years when I was with the UTM Water Research Alliance. Yes?
Sorry. I don't, is it moving your?
Oh, no, still here, still on the same slide, 19 slide.
Oh, still on the same slide, okay, sorry.
Still on the 19 slide, 2014, 2017. You can see this Professor Richard Hawkins slide, right?
Okay, right. So, okay, sorry.
Okay. So 2014 and 2017, I devoted myself to include the statistics during the model calibration. And then at the end of the 2016, I found a way to derive the curve number. So for all of you who are using HEC product, HEC-RAS, HEC-GeoRAS, HEC-HMS products, there is no need for you to choose the curve number as an input anymore. So for SES practitioners in Malaysia, in any of the federal government agencies or state agencies, if you are still choosing the curve number based on the land use or the land cover that is considered to be the outdated method, I will share with you a few of my past publications as well. So from 2020, there's a break over there with it. I thought that my job was pretty much done. The local developer in Malaysia actually picked up the methods during my consultancies in Malaysia. I tried to relook at the curve number again, and then I started phase two of the research of the curve number. That's why you can see down here in 2021 to 2023, there's a revised curve number runoff predicted model being involved. This actually came from the two NARIM consultancies that I had. First one that I joined the UTM Water Research Alliance was on the climate change, impact on the agriculture. The second one, after I joined the UTAR, I served NARIM one more time, again for flood damage curve analysis in the Peninsula Malaysia. And then once again, I saw the application of the curve number. So if you think about it, there are some of the statistics over here. In Malaysia, the surface runoff is actually contributed about 97% of the total water demand. So to hydrologists or the water resource management, this is considered to be a very bad news. We are blessed by ample amount of rainwater, but it becomes a runoff. Then sooner or later on, that fresh rainwater will become polluted, washing down the drain. And if it mixes with all the trash and chemicals and then the engine oil, debris and everything, it becomes non-drinkable unless they spend a lot of amount to treat the water. Then it slowly finds its way into the river and then go through the ocean, and that's pretty much the end of it. And for the rapid urban development, and the human activity, we keep on calling it the anthropogenic activities, are the main culprit, and then the cost for the flooding in the downstream. No choice. The price of the urbanization and civilization that we are paying. Once you develop the upstream, then the downstream part basically will be impacted, will be affected. So the back to the fundamental, or my fundamental research basically is going back to the beginning of the source to have a thorough understanding of the rainfall runoff process, to see that the thing that we use, in my case, my research only focus on the curve number. If the federal agency, state agencies, or some of the government agencies are using the curve number, you are at a high risk at this point. I can give you a quick conclusion. First step of committing a type 2 error. Curve number in Malaysia, from my experience, verified with the local regional rainfall runoff study, has found that to be inconsistent. Sometimes it over predicted the runoff, sometimes it underestimated, sometimes it do both. Later on, I will show you one of the case example that I first found out the study site in Malaysia, and how it predict the runoff inconsistently. So SES practitioners, according to the handbook or the guideline, they have to select a curve number to start the whole process. Leading a lot of SES practitioners are doing the try and error, tweaking the curve number. Now, I'll just look at the land use land cover. I think that based on the descriptions of the SES or the USDA, United States Department of Agriculture handbook guideline, I think this curve number should be 76. And then it didn't really predict the runoff correctly. Then you start guessing, should I use 77 or 78, or should I actually go back to 74 and 72? So it becomes like a guessing game. When you tweak it eventually, finally with the set of the rainfall runoff data, or the historical runoff data, that you already have achieved 80 to 90% of accuracy, you therefore declare that this is the end of it, and therefore the curve number for your study site should be 78. There's not much of the science in that sense if you actually do the try and error. Also, of course, it lacks the statistical justification. Those of you who use the statistics, you have to know that we have to declare a model to be usable from the alpha of 0.05 level above. Basically, have at least have a 95% confidence interval to use it. And if budget is not a concern, or there's a high amount of a huge construction projects involved, in this case, we talk about the hydro or the flood mitigation control structures, maybe you push the alpha level a little bit higher to 0.01, reaching the 99% confidence interval. So the more that you push to the lower alpha level, or to have a higher confidence interval, the cost basically goes up. So is there a way that we can actually derive a statistical significant curve number so that we can calibrate this curve number model to use it? The equation shown in the red over here, this is a simplified version of a conventional curve number. A lot of textbook basically just use this. Do not use this anymore. Trust me. You have a very high chance to commit the error in the Peninsula Malaysia. One of my publication into the mathematics journal basically argue all the way through with the mathematics professor before he published. So here is the whole story about it. So let's go to the history lesson a little bit. Back in the 1940s, the SES Soil Conservation Services, now known as the USDA, US Department of Agriculture, had to solve a local flooding issue problem. And in 1954, they announced that they are using this basic fundamental rainfall runoff model, and then they simplified. So the reason of simplification is this. So what you're looking at, figure 1 over here, this was the original and the beginning of the so-called the curve number. You only have about 112 data plots over here. They plotted onto the graph, and then they feed it through it. And on the y-axis is the IA, the initial abstraction. And for those of you who are not familiar with the initial abstraction, these are the amount of the rainwater that really never really reached to the ground, hanging on the tree. It could be evaporate or actually hanging on the tree stem or the tree trunk. And on the x-axis over here, this is the total abstraction. We can also call it a layman term, the ability for the ground to absorb. So you have a y-axis and the x-axis correlation over here. They draw a line. They say that because more than 50% of a data point fall into this line, and the relationship between the correlation between the IA and S is 0.2s. Bear in mind, all this documentation and the decision to come out with IA is equal to 0.2s has been lost. So this is the last documentation process. So if you look at the fundamental curve number rainfall runoff model, whereby IA is equal to lambda. As lambda is just a correlation between the IA and the S. And then from this graph, they decided that the initial abstraction is about 20% of what the ground can absorb. So IA is equal to 0.2S has been proposed. And if you substitute into IA here and IA here, you can simplify into what we call the conventional SES curve number that exists in every single hydrology textbook. After today, if you found a hydrology textbook with a curve number chapter, if it doesn't have this this formula on it, let me know. I still have not been able to find one of the hydrology textbook that talk about curve number without heavily promoting about this equation and then this simplified model. And then later on, there's a formula to calculate the curve number proposed by the SES. So I'm going to carry this portion of the information throughout some of the slides so we know that what we talk about, because later on I will talk about the lambda over here. So UTM, Water Research Alliance, keep on joking around, say that I'm the lambda man right now, because my PhD basically focuses to find the lambda for Malaysia, for Peninsular Malaysia. Lambda, again, in this case, if you look at the 1954, the original graph, this is the correlation between the y-axis and the x-axis of two important parameters, IA, initial abstraction, and then S, what the ground can absorb. So 1954 decisions, SES basically proposed based on this graph, the correlation between IA and S should be 20%, and therefore IA is equal to 0.2S has been adopted. Bear in mind, all the documentation, MITI minutes has been lost, so there's a lost documentations. Even Professor Hawkins went and then interviewed the surviving committee member. The committee member said they don't really remember there was actually a MITI minute at the time because we were in a rush to come out with the field application formula that the hydrologist or the hydro engineer can use to solve the regional flood problem back in 1954. So we have a documentation loss problems, but the handbook goes on. All the textbooks, it's still giving you the textbook example, tutorial material, how to use the so-called the simplified formula and keep on assuming that lambda is equal to 0.2. Professor Richard Hawkins, just now I mentioned, got the ASCE fund, but totally exhausted throughout the field verification. He haven't really covered half of the United States and then exhaust all his fund. So the questions that he passed on to me in our collaboration is that why does this correlation has to be 20% or 0.2? And why is it proposed as a constant? Can it be a variable? If we let it change and don't fix it into the 0.2 and go back to the fundamental SES curve number model, would it be better? So I took over the collaboration and then the challenge that I'm actually inputting and then incorporating the statistical assessment methods to calibrate the model. And then I found a way to derive the curve number. So there's no need to select any of the curve number as an input. You can actually, based on the rainfall runoff data set, and you can derive the curve number for any of the watershed or any of the catchment. So this is the result of the Professor Hawkins. Professor Hawkins SRC's funding. There are 50 states in the United States of America. He didn't even cover 50 of it. The official results, to be confident, actually only 24, even though that his work span across 27. California, it's all the way over here. Oregon, Virginia, Canada. This is so-called the West Coast. He didn't even have a chance to come to this site. So the use of the statistics to calibrate the model at the time became very important to him when he passed on to me in 2015 and 2016. So the questions that I have to bring back and then have to ponder upon when I was with the UTM, Water Research Alliance, is this lambda value, is it for USA only? Is it possible that it's not even applicable in the other part of the world? And because the American introduced it, you know, we just monkey see, monkey do. We got the textbook, we read the tutorial, we duplicate the methods. A lot of agencies or the consultancy firms are using the HEC product, HEC HMS, HEC RAS, HEC GeoRAS, because there's a need for us to do the GIS with it. And then those are open source. HEC product actually is developed by the US Army Corps of Engineers, or the federal agencies. Equations are basically intertwined and then they built in with it. So my questions at the time is, if this is actually regional specific, then it will really committing the type 2 error, having a huge risk, blindly believe that something that might work, or once upon a time that it worked in the United States of America, might work, in our case, in Malaysia. So the studies that I have is I started conducting the literature review and see that what about the study outcomes by other researchers when they publish the journals. So in Europe, we have few of the countries. You can see Greece, you can see Italy's, and then you can see some of the British researchers went to different part of Europe, and then they reported that lambda is not 20%. It's not equal to 0.2 coefficient factors as reported by the SES. And it's also in line with Professor Hawkins' United States results that majority of the lambda value should be less than 5%. And on average, it's 5%. So now you can do a little bit of an estimate. If lambda is not 20% as proposed by the SES, and based on a US re-verification, even 27 states, it's about 5%. 5% to 20%, how many you are off already? Should be sending chill down your back. So if you go to India, India was the only country with the India researchers that reported that lambda 0.2, okay, over there. And then lambda could be greater than 20%. The highest lambda was reported by the Indian researchers. They reported as high as 30%. But the study plot was small, and then the rainfall runoff sample size was not huge. You can do your literature review. You can search about on that part. How about in China? China also reported that lambda is not 20%. It's not 0.2. And then it's also less than or equal to 5%, which is also in line with Professor Hawkins' study. So when we switch to South Korea reported also the similar incident. So at the time when I conducted the literature review, combed through the journals from the international researchers, now come all the way nearer and nearer to Malaysia. Even in the Australian researchers, they reported the same thing. So it looks like Professor Hawkins from the US reopened this can of worms, and then the researchers start verifying this SES curve number model one more time, and then they all found out that the assumption was wrong. We really have to go back to the fundamental. And all these researchers basically are reporting saying that if the lambda value can change, don't fix as a constant. So over here, I compiled 27 journals back in 2016. You can see that the percentage of the 0.2 or larger than 0.2 was actually they were the minority. A lot of them basically goes below 0.05 or smaller. So these are the lambda distributions. So if it is allowed to change, many of the researchers in any of the country actually reported that it will improve the runoff estimation accuracy of the model. Rainfall, we cannot change. It's from God. Okay, whatever down there, you receive the rainfall intensity, large or small. If you measure the amount, if you measure it correctly, you have the P data, rainfall data. Now it's a runoff, water level stations, and the study plots, let it be whatever. If you measure it correctly, and then you wait long enough, there's a soil saturation, non-saturation issue. Those are the details that you have to worry about. If you repeat those experiments, it's highly probable you have a high chance that you will find out that this lambda, the correlation between the initial abstractions and then what the ground can absorb is really not 20% of it. It's a lot smaller. So in general, in line with the Professor Hawkins' study outcomes in the United States, before you reach the grounds, the initial abstractions should be about 5% of what the ground can absorb. So we see after I rearrange my so-called the journals, we can see that 36% of the research studies basically were recommended to derive and adjust with the local regional rainfall runoff data and let it become a variable, vary away from 0.2. Don't fix it as a constant. 8% of them, two out of 25 journals saying if we still use 0.2 and follow the simplified equation model, we can get acceptable result. Now down here, it's the huge batch of the 4 out of 25 journals saying that if you don't calibrate the model, it will overpredict. 6 out of 25 say you will underpredict. 9 out of 25 say that it's inconsistent result, which means that in the same study site, same catchment or the watershed, you will see some rainfall event that the runoff will overpredict, while some of them it will underpredict. Later on, I will share with you one of a study at the journal that I published actually in Malaysia, where catchment site we actually experienced this situation. So Malaysian study, or my early part of a study, basically fall into the inconsistent result category. So I became the number 10 out of 26 of this group, saying that, my goodness, that even at the same site, the land use, land cover is not changing. If I stay over there and then just measure the runoff from the rainfall, sometimes it overpredicts, sometimes it underpredicts. So the model become highly unstable already. So here's the roadmap based on my literature review initiated in the United States of America, go to the Europe and then go to the India and then China, South Korea, to the Australian, or finally back to the Peninsula Malaysia, or to the Malaysia. That's where I'm at. So the questions from 2015 onwards, for me, I keep on asking the questions that, is this a regional specific model or the lambda? If it is possible, then will the foreign study results mean anything anymore? Because we are Malaysian catchment and Malaysian watersheds. Can it be a meaningful reference study outcomes or the result anymore? How about the curve number? So if lambda change, will curve number change as well? So I already set my goal and objectives that I will need to do everything in the reverse way. Instead of choosing a curve number, I must derive and calculate the curve number. So here is the fundamental. So if you're going back to the fundamental, here is the fundamental, the equation rainfall runoff model. Australian professors basically did an assessment for it, saying that this model is actually quite stable. And then we call it parsimonious because it doesn't use a lot of a variable. P is the rainfall and Q is the runoff. So you're only dealing with 2 variables over here, making it very cheap. If it is calibratable, usable, then it's a fast and furious solution to the rainfall runoff situation. The only thing based on the literature review is that we better don't assume that lambda is equal to 0.2. So on my case, basically the first paper that the challenge basically need to demonstrate or to propose, like a salesman, to demonstrate the methodology that is able to reassess the initial 1954 SES claim. The choice of the statistic that I used was the non-parametric inferential statistics, set up a null hypothesis to basically check whether lambda is equal to 0.2 or not, using the regional local rainfall runoff data. This is to avoid the type 2 error, and then also aims to derive the regional specific curve number directly from the rainfall runoff data set. By doing that, I'm able to calibrate the whole model successfully. So these equations can no longer be blindly adopt for it, because that it has a built-in suggestion with the proposal that lambda is equal to 0.2. So based on 1938, when the SES started the whole thing to 1954, the purpose is to develop an equation model to the left over here, aim for the flood control purpose. And they propose that lambda is equal to 0.2. When IA is equal to 0.2s, and you substitute into this equation, it further simplifies to the equation in the red. So 2015 onwards, I keep on using the inferential statistic to assess it based on the literature review result that I have. So the null hypothesis that I set up is this model is applicable globally in order for IA is equal to 0.2s, the first proposal to be correct, to simplify the fundamental model. Malaysia is part of the global map, the location that we located on the Earth as well. So if this null hypothesis cannot stand true, this equation in red basically will be in huge questions. So I'm reassessing also the constant parameter. If it is not constant, if I can prove that it can be a variable, then I can change lambda to any other value that I want. Basically, I can optimize the model. So the statistical assessment basically aim to solve the issues about the inconsistent rainfall runoff results. So at the end, I pronounced that actually from the first batch of the research come out that the model should be the nonlinear, and the lambda is not a constant value. Now hypothesis basically being rejected alpha 0.01 level, that the model, the simplified model, the red equation is not applicable globally. IA cannot be equal to 20% of the S. And based on the 99% confidence interval for the first Malaysian watershed that I test out outside of a Skudai watershed, I went to the Malana site nearby to the Johor UTM area. We found out that lambda is already not 0.2. Lambda 99% confidence interval based on the rainfall runoff data set was very low, about 0.00397 to 0.15. And it will have a huge fluctuation between the low and the high limit, about 3,773%. And in this 99% confidence interval, 0.2 does not exist. So the simplified SES model does not apply to the Malana watershed near to Skudai area in UTM. The optimized lambda model at the Malana watershed was reported as 0.15 with the confidence interval of 99%. So with that, can I actually derive the curve number? So in order to achieve that, this fundamental equation need to be rearranged. It looks simple right now, but we need to isolate the S. Need to solve for the S in terms of the function of the P, Q, and lambda, rainfall, runoff, and then the coefficient, correlation coefficient. It's a huge process. If you look at some of my journal, which I provided the link later on with it, it will show some of the derivation steps to isolate from this fundamental equation into this equation. This is considered to be the S general equation. It's been solved by Professor Hawkins and being solved by Professor McQueen as well. Those of you who are familiar with the hydrology textbook used by quite many of the public university, white cover, actually written by Professor McQueen, he also show a different variation of a S general formula. As you can see, this is the closed form equation that S is equal to PQ lambda, all successfully been isolated. So as long as you have a rainfall runoff data set, PQ enter here, PQ enter here, PQ enter here, you just have to optimize the so-called the lambda value. So lambda becomes a variable right now. The only reason that we have to suffer through this is the Professor Hawkins saying that once lambda deviate away from 0.2, curve number can no longer be calculated with the so-called the SES curve number formula. So we have to convert to bring it back. And then the closed form equation of the S general formula is the only way, like a passport or the visa, to bring it back to the same scale again. So by using this S general coefficient, the S general formula, you will be able to correlate the new lambda value. In this case, in the Malana site, outside the UTM, new lambda value is 0.15. We can correlate back to the conventional 0.2 scale using the SPSS with this equation. So SPSS actually identified the power form, saying that based on the rainfall runoff data set, every PQ data set you put inside, you will be able to calculate the value out of it. Now we know lambda is equal to 0.15, so 0.15 here, 0.15 here, 0.15 here, and then put in the PQ data set, you can have the S lambda value. So if you have 20 rainfall runoff data set, you have 20 S 0.1 value on one side. And if lambda is equal to 0.2, with the same corresponding PQ data set, you can generate another 20 pair of the value using this closed form equation. And using SPSS, 20 pair under the lambda 0.15, 20 pairs under the 0.2, you can correlate them. Using this correlation equation, we can calculate the curve number again. So this is the only way that I know at this point that we can do it successfully in the reverse manner. We no longer need to follow the SES and the USDA handbook guideline that we must choose a curve number to start. Curve number became the last part. Given the rainfall runoff data set, you can find a statistically significant lambda value to represent your catchment or the watershed. And then after that, we can actually correlate to the conventional number using the closed form equations and then derive the curve number. So those of you who using the HAC product, HFMS, HACROS, and HACGeoRAS, after you calculate this curve number, you can actually input it into your software program. So you no longer need to go out and then look at the land use land cover. Land use land cover, there's a lot of publications saying that, you use the LiDAR image, you use the satellite image. My question to challenge that philosophy is that, can you really buy a car, new car or the used car, by just looking at the outside of the appearance without really test driving it? You don't do that, right? Then why would you want to look from the satellite from a very high above? Oh, this one looks like a forest. This one looks like a semi-forest. So it should be somewhere between the forested watershed and then the semi-developed watershed situation, and then guess the number. There's no scientific sense of doing that. So ground, later on I will share with you one of the publication. I proved that even in Malaysia, the land use land cover has not changed. And then when it rains and then when the grounds become saturated, it's just about to flood, curve number keep on changing. This proves that GIS or the LiDAR or the satellite imaging, by observing the land use land cover, is a very dangerous practice as well. That land use land cover, even though it doesn't change, you cannot see what's under the ground, the geological formation, the soil absorption ability, and everything else. When it becomes increasingly saturated, runoff situation change already. So don't look at things from the outside, look at the outside appearance only, and then make a decision and select a number. That is a very dangerous practice. So I'm personally more comfortable by deriving the curve number with the endorsement of the statistics to tell me that at least that my curve number now are within a 95% confidence range, 97% confidence range, or 99% confidence range in order for me to proceed with my consultancy project or proceed with my research. So S general equation becomes the center of the universe at a time. That when we try to calibrate, I share these methods, the statistical methods that I'm able to calibrate it to show the confidence interval of the lambda, and therefore my curve number also has the confidence interval. Professor Hawkins has introduced another method when everything failed. He proposed using the asymptotic curve number fitting. For those of you, the SCS practitioners, this is actually to remind you that the asymptotic curve number fitting methods actually has its own flaw. And the journal link that I gave you, a few of them actually have included a benchmark comparison with the asymptotic curve number fitting in the Malaysian watershed, whereby the accuracy becomes lower as well. Bear in mind, these were developed by Professor Hawkins, but based on the US watershed experience. Professor Hawkins was shocked when I presented the DID hydro procedure 27, the highest recorded rainfall. The amount was actually reaching the 227 mm per stormfall event. To him, it's just like, this is unbelievable. He had never seen a storm event that were recorded the rainfall depth more than 100 mm. So 100 mm and 150 mm to him, you were basically flooded the whole United States already. So the asymptotic methods basically has been benchmarked, and this is one of the thing because Malana site was the first one, first major study sites that I fully implement all the methodologies. I was able to show, in this case, the top line is a Nash-Sutcliffe index, and then the red line is the residue sum of square, and then with the curve number. So you can see that the curve number, basically, if it is keep on changing to the Malana site up to the certain point, then it will reach the optimum, the situations that the RSS is not too high, and then the Nash-Sutcliffe is actually dropping already. So at the high part over here, the optimum curve number for the Malana site, if it is actually set around the 88.9, I was the first one to introduce a curve number with the decimal point, that you will have a highest Nash-Sutcliffe for the whole model to predict the runoff amount with the lowest residue sum of the square error. So this is another visualizations that the risk of adjusting or tweaking the curve number. Curve number is a very sensitive parameters. You can see 88.9 to the 90. Suddenly, if you just move 1 to 2 notch of the curve number to the right hand side, what will happen to your error? Your RSS basically just keep on shooting up in an exponential manner. So be aware for the SES, the practitioner. This is another visualization view when lambda is allowed to change. Starting point is 0.2. If we keep on reducing it, you can see the model bias, basically scale, and the model RSS. The model, if we actually allow to reduce the lambda value from 0.2 to the lower level in the Malana site, the model RSS prediction error just keep on dropping and dropping and dropping, reach to a certain point, and it looks like it will be stabilizing again. And then here's the model bias value. At the time, I add in the third challenge, that the model prediction that I calibrate the models, the model overall bias should be near to 0. So it does not only work with the specific of the rainfall runoff data set that I was using, it was able to cater to any of the future data set. So here is a comparison. I've compared with the Professor Hawkins using his asymptotic methods and the proposed new statistic calibration methods compared to the conventional SES methods. You can see that all of them actually are deriving different kind of the curve number. And then you will be able to find out at the Malana site that the error is the lowest, and then the Nash cyclic model accuracy index was the highest, and then the model error residue was actually the lowest. So conventional model, if you're actually not doing it, you can see that how many times of the model residue, basically model error that you will have compared to the calibration methods. So this was the first major pilot study site that I did at the Malana watershed. And as you can see, I start experiencing the J-curve pattern already. Every time a J-curve patterns come out, it's actually showing that the uncalibrated model is inconsistent. Meaning at this case, anything to the left-hand side, the lower rainfall amount, you will see that the uncalibrated conventional model will over-predict to the wild, then it will start under-predict, then it will start over-predict again. So you have three different zones, same watershed, same catchment, but based on the rainfall amount. X-axis is the P amount. Small rainfall amount at the beginning, runoff will over-predict. Then in the middle, it will under-predict. Then when the rain falls really, really hard, it will start to over-predict again. So this is the visualization graph. Every time you have a J-curve patterns coming up, it shows that this is a major warning sign for the SES practitioners that the SES model will inconsistently under and over-predict the runoff amount depending on the rainfall. It's very dangerous already. So modeling specific things, I'm able to also adjust. So these are the adjustment equations, QV. Once I identify the J-curve, I'm able to correct them, which means that I can take the conventional equation, in this case of the Malana experiences, minus the QV. For rainfall amount less than 16 mm, the conventional equations need to be deducted by the first equation. For the rainfall amount, a rainfall depth that is greater than 16, the adjustment equation should be this. So those SES practitioner, you are using the HEC product. If you analyze deeply enough with the methodology, this is the only way that I found it quite useful, is that you can map out the rainfall runoff, and then you see the J-curve, which means the next thing is make an adjustment. And then whatever equation, if you actually cannot, or you bought the software that the lambda 0.2 is built in, that you cannot really change it at all. You can only take the result generated by the software and then do the minus adjustment. So it looks like a lot of work, but at least you don't have to spend extra money for the software. So that's another objective that I promote. Software, you already invest the money, and then you already been trained on to it, but you just have to know based on this research outcome sharing that J-curve basically telling you that it's performing inconsistently. It's time for you to do the adjustment. Don't blindly like punch in the number into the calculator, whatever the calculator tell you, or the runoff estimate amount generated by the software. You just take it and then do the drainage design. That is the perfect recipe for disaster. So for the applications, when I present this in one of our conference, Malana watershed in the Johor is 21.12 kilometers square. People ask me, why even bother? If I didn't change it, what would that be? So I presented in another way about the Olympic-sized swimming pool. So on average, on the over-prediction trend, on average, over-prediction for the model, if you don't want to change it, you will over-predict by 7.04 mm rainfall depth. The understanding it's based on the rainfall events. The over-prediction is about you over-predicted 60 Olympic-sized swimming pool volume of the amount. So if you use it to build the drainage, you will waste a lot of money. And the under prediction is also the danger part of it. Under prediction, in this case, on average, the under prediction is about 0.8 Olympic size swimming pool. So based on this kind of the information, then you can do the assessment of the under and over design risk in this case. So in this case, I believe the J curve pattern, I call it J curve because it looked like a J curve. I don't want to call it Nike because it infringed with the Nike logo. So this is actually non-linear error. So in this case, a few conclusions can come out already, pretty much based on this experience. It's possible to adjust. If you're using the software, just take it to deduct it. Equation of the red simplified conventional model has been X out already. You have to go back to the fundamental, find your own lambda value, and then derive your own rainfall runoff prediction model. So by reaching that stage, I published some of the journal prior to the graduation. After that, over here, selected 4 to mention about 2019 in the Water Journal. This is basically for the China. If you click onto the link over here, I've clicked on all of it. I can show it to you later on for the China watershed. The Chinese basically did not fully derive this method. So they just assumed that 0.05 as reported by Professor Hawkins will work well in China and then just put it in for the prediction. Sungai Kerayong, I have 1 journal on it, and then 2 journals, 2021 and 2022 into the mathematics. Type 2 error assessment has been done using the DID hydro procedures for the entire Peninsula Malaysia. And the parsimonious urban flash flood prediction model done with inferential statistics also published into the Q1 Mathematics Journal based in the 2022. This was a shocking research outcome showing that even the watershed is the same, the rainfall, the land use, land cover doesn't change. The curve number just keep on changing. So the China watershed, I'm going to talk about here. IEEE, Sungai Kerayong, back to our homeland. You can download it. Peninsula Malaysia, type 2 error, reported that at alpha 0.01 level, that for the Peninsula Malaysia, using DID hydro procedure, the curve number should be 72.58. Yes, in order to achieve accuracy, curve number doesn't have to be integer anymore. It basically can come with a whole number. And the 99% confidence interval range using DID hydro procedures, rainfall runoff data set, saying basically have derived that the curve number range for Peninsula Malaysia should be somewhere between 67 to 76. So this is something that I've found out using the DID hydro procedures rainfall runoff data set to find out the experience with the Peninsula Malaysia. Of course, that for 1 kilometer area, how many of the water will be over predict and under predict. You get more than welcome to download this. I think it's 26 pages or something. Reviewer at one time complained that this is almost like a technical report already. It consists on some of the formula generation. So type 2 error, this one is actually considered to be quite comprehensive with a tutorial on the site, how you actually can come out with the 3D model. I basically have generated the 3D model for Peninsula Malaysia. Yes, so you can visualize the red zone is where the amount, the runoff amount will be under predicted, and then the so-called the mountain or the hilly side is where the if the rainfall amount starts to increase, then most likely you will start to over predict. So you can download this and then you can read this through. If you run into any of the technical problem of understanding of how to use it, you're more than welcome to write an email to contact me. And I've also proposed a way to correct the software outcome using the DID hydro procedures informations for the entire Peninsula Malaysia. Now bear in mind, climate change, which means that it will change into the future. So all this information basically will soon to be obsolete if the rainfall runoff information basically keep changing. The whole model basically need to be re-derived and then reassessed again. So this one also benchmarked with the asymptotic curve number fitting methods proposed by Professor Hawkins in order to benchmark its results. So you can, this is a free open access journal that you can take a look at it. So asymptotic fitting methods proposed by Professor Hawkins versus a new derived lambda model for ourselves, for the Peninsula Malaysia only, the accuracy, the errors, and everything else. So you can download this journal and take a look. Another mathematic journal, this one is a shocking discovery. Urban flash flooding issues has nothing to do with the rainfall intensity. It's all rely on the ground saturation. When the ground is increasingly saturated, flood will come very, very soon, even though the rainfall intensity or the rainfall depth is not high. So in other words, in the layman term, if it start drizzling non-stop on and off for more than 3 or 4 days, you know, the rainfall intensity doesn't need to be high. You just keep on lingering the rain cloud over our head. Flood is going to come soon. So based on this information, this is done, I believe, in the KL area, the Kayu Ara area. So you will be able to Sungai Kayu Ara, Sungai Kayu Ara watershed. And this was sponsored by one of the developer as well, especially demonstrating the interest into the Kayu Ara development project area. Funded this research on the site, has been supporting my research for a few years already. I found out that even the land use land cover does not change or did not change as the rains goes on. The runoff estimate or the curve number will keep on changing. The value will keep on switching already. So it's very dangerous for GIS users basically to observe and just look at the land use land cover condition and situation and then guess what is the number. There's no guessing involved over here. When you guess, sometimes it works, sometimes it might not work. So please download this info, this journal. If you take a look at it, for you who are interested into learning about the ground saturation, how does it impact with the calibrations of the SES model, download this journal will do. Last one, later on I'll talk about the revised curve number. So with all these regional specific, I was going to end this research study again. Is that all? That is done pretty much. I no longer rely on the curve number as an input. I can derive it. If you ask me how confident is my result, I always say that don't ask me, just look at the statistics. If the statistics guarantees a 95% confidence or 96% confidence based on the rainfall runoff data set that we work with on the hand, it should be 95% accurate. We want to avoid the type 2 error. Basically, we need to rely on something from the inferential statistics level that can give us an inference before we do the design and everything. These equations, simplified equation, lambda 0.2, definitely cannot be assumed anymore with it. And then it's possible that we can adjust the outcome for the SES practitioners. Those of you who spend money into the software, don't worry about it. There's always another way out. You don't have to dump your software. There's a way that we can actually train you up. You can download my journal, take a look at it to see whether you understand the technicality. If not, later on, that please take a screenshot. I believe the IEM organizers also share my PDF slide with you. You have my the email on it, or else you go to Universiti Tunku Abdul Rahman UTAR staff directory. You'll be able to find my email as well. Now, what triggers the MoHE fundamental research grants into the second phase of the revised curve number runoff prediction model? After I asked myself, is that all? Was that when I look at 2020, You know that funny things happens during the COVID. Now you lock yourself into the room, you cannot cross the regions and everything. So I start looking at the historical data again, the SDS original data set. So in front of you here are three graphs. Over here, left-hand side, this one was the oldest graph that you have from the NEH, National Engineering Hydrological Textbook, the handbook used by the SCS back in 1954. This one was perhaps the oldest surviving document PDF. If you download it, you can download it. They actually archived it in 1960 something. Look at the x-axis and the y-axis. And here's another handbook version, second one. Look at the x-axis and the y-axis. This is not a normal scale graph. This is a log scale graph. So when I log myself at home, I start thinking, log scale graph means what? Once upon a time, you know, that laptop or the high computing power desktop is not available. So people use the log paper. You have a normal scale and a log graph, and then you have a log graph. Log graph in today's terms means what? It means power function. People normalize their data plots and then plot on the log scale graph. If it is not on the log scale, it should be a power function. Why are we talking about this now? The question comes up. Even if IA is equal to 0.2S was valid as proposed by NCS back in 1954, why did they take it directly without taking the anti-log form? How come they can directly substitute IA is equal to 0.2S into the fundamental this equation and simplify? What happened to the anti-log form? Plotting, normalizing the data, it's only one of a technique. After you find out that what will be the best correlation or whatever, you can download my journal. You can find out that Professor Hawkins and me basically reassess, and then we found out that using the 112 scattered data points by the SCS, that the best correlated equation before we take the anti-log form is not 0.2, it's 0.111 or 0.112S. Back in 2020, during the lockdown period, I asked myself, how come we don't take the anti-log form? If we take the anti-log form, it's no longer IA is equal to lambda S. It should be IA is equal to S to the power of lambda, considered to be the basic power equation form. Some of you, if you remember, oh, another anti-log form basically comes up with the constant. I don't prefer to use that function because with the constant, which means that somewhere on the y-axis over there, you have a positive intercept of a y-intercept, which in the hydrology, there is no implication. And if you try to simplify into the rainfall runoff data set, your rainfall data set will be either be added or being subtracted, which is also meaningless at this point. So the simplest power form after taking the anti-log form is IA to the S lambda. So these equations is no longer valid. The closed form equations now will only work if we are using the linear correlation to simplify the fundamental equation 1. If we take the anti-log form, IA should be equal to S to the power of lambda. We need a new general equation. So that's how I got my FRGS. I was lucky enough. In the 2021, I got my FRGS, 2-year FRGS with supporting full funding with one of the master's students. I quickly pick up one of a mathematics graduates because I know that I will heavily be dual into the equation simplifications and then the rederivations. So this is the second steps of the discovery after all the previous publications. So in January 2023, almost end of January, published one of the journal into the Water Journal. Basically, we call it the revised curve number runoff methodology for the improved runoff predictions. And let me share with you. Saw the last article just now. The revised curve number rainfall runoff equation methodology published in January basically challenged that if we are not using the so-called linear function and we are taking the anti-log form, IA should be equal to the S of the power. So using this equation, can we reduplicate everything that we have and then simplify it again? So that was the challenge. So if you look at the appendix, this one was meant for the teaching material as well. So I will just go to the appendix first. If you download this journal, you will see from the appendix A some of the lecture material of which I propose to use IA is equal to S lambda to basically re-simplify this equation. I try to get a closed form equations by separating S on one side, PQ, and then lambda to the other side. But to date, I'm unable to find a closed form equation. Since there are no further simplification, the simplest form is actually put in the A1, and then we have to rely on the numerical analysis technique. So there are tutorial inside these journals basically saying that how to find it and how to calculate the curve number. So appendix C lists out few of the steps of how to generate the result and how to derive the curve number. It can still be done. It can still be done because my FRGS basically will come to the end in the September this year. So this is the reporting time. So you will see that it is a comparisons. I have used DID hydro procedure 11 dataset, the latest one, released in 2017. DID hydro procedure 27 dataset, released in 2010. I combine both of the dataset. So total, I have 701 rainfall runoff dataset, making the largest rainfall runoff dataset analysis in Malaysia. BIODATA coming in, Chian coming in. I grabbing and then reassess the Greece and then China with the power form, and it all work. So on the phase 2, instead of using the linear form, now we have a power form. So we ought to take a look at the this kind of a study and argument. Over here, we talk about the Professor Hawkins and mine. So reference 16 and 17 basically talk about our assessment on the original data point used by the SES, why lambda is not equal to 0.2. If they want to insist if IA should be equal to 0.112 or 0.111 S. But if you take the anti-log form and then simplify the whole equation, it should be IA is equal to S to the power of 0.111 or 112 into the equation 1. So that's what happened when I was locked indoor during the COVID. So this is the result. One more journal is under the rebuttal at this point. First rebuttal, we sent it in already. It's an extended application of using this the power model to assess and predict the decadal forest runoff in the Peninsula Malaysia using this data set. Hopefully the rebuttal will be successful, and then it will be published soon. So you have 2 of the journals coming out using the revised model of it. So in this case, equation 1, now the general S general equation, there's no closed form equation, cannot solve. I couldn't find it at this point. I cannot isolate S and PQ and a lambda to one side. This is the closest form, and we have to use the numerical analysis. So if you refer to the journal appendix A, and you will be able to see one of the derivation process, and then there's some of the tutorial with it. So I've shown to you that I've tested with the DID hydro procedure 11, 27, combined both of them because I want to make the rainfall runoff data set as large as possible with BIODATA Chian in Malaysia, tested in Greece and tested in China. Works well. So what's next after this? Extended application, decadal runoff assessment in Malaysia. This one is under the rebuttal. One of the reviewers suggests to revise the title, so I don't know what it will end up with. I have been approached by the US EPA, who saw my publication in the Mathematics Journal, to join them to derive the regional specific curve number into the EPA site for the EPA project. And then I've ongoing discussions with the developers and then the state governments, but I will not be able to disclose more with it because soon, if you materialize, it will be under the NDA part. So we're coming to the end of the research outcome for it. So the journey for the urban flash flooding and the revised curve number at this point looks like the fundamental research. When I go back to the fundamental research, there's a part 1 and the part 2 of the study. Something from the very fundamental, we always have to ask the questions that why am I using that equation? Do I have any of the choice to do it differently, to assess the result on my own and everything else? So these are some of the ending message that I try to pass on, try to share my experience with all the participants. And this is my email. My email is basically my whole name. I always laugh that I have the longest name in UTAR. So my name with no space, Ling Lloyd at utar.edu.my. You'll be able to email me. You're more than welcome to contact me for different kind of the collaboration research. And then if you still don't understand from those 5 journals, it was written in the format that I can use it as a teaching material, as a tutorial material for my students, undergraduate students and postgraduate students anymore. You're more than welcome to contact me so that I can clarify all the information as needed. Basically, it's almost 1 o'clock, and then we will have reserved 30 minutes of the time before the end of the webinar today for the Q&A section. I guess this is the right place to end already. I'll pass it back to the IR Asa to see if there's any of the questions, or if you want to take a short break. I'm open to the suggestions.
Okay, thank you very much, Engineer Dr. Ling Lloyd, for the very interesting study and sharing. I'm sure it is very useful, and hopefully it will be a situation that, especially in our local region, regarding the flash flood issues. Okay. Okay, I think it's a good idea. Maybe we'll take a 5 minutes break before. Is it okay?
Okay, okay, good.
Maybe take a 5 minutes break to collect the questions. So the attendees, you can put in the questions in the question box and in the application in the GoToWebinar. And after this, we'll go through the questions. Okay. Okay. I think we'll take a break to allow questions to come in. We'll start again at 12:55. 12:55. Please put in your questions. Okay. We'll take a break, and after this we'll go for the Q&A session. Okay. So now it's 12:55. Dr. Ling, Lloyd, are you ready to take questions?
Yes.
Okay, thank you. Okay. So the first question is from Mr. Muhammad Afizi, and his question is how about the type of soil of A, B, C, D? Is it not mentioned during the selecting of the CN or the curve number? So I'll
Okay.
repeat again, this soil A, B, C, D. Okay. You?
See, at the end, if we look at the outcome, your soil selection of the ABCD basically will affect the runoff amount. So one of the journal that I would like to refer to you is actually the parsimonious. I have to scroll up a little bit, make sure that this journal. Formulation of the parsimonious urban flash flood predictive model with the inferential statistics. As I mentioned just now, this watershed actually is very interesting because the rainfall runoff amount that it collected is enough for me to separate into 3 batches of the saturation level. The soil on this watershed is consistent. But as it becomes more of the increasing saturating, the runoff number and everything start changing already. So which makes it less meaningful if we actually try to spend time and effort to classify the soil into the ABCD. You classify after you successfully have identified the soil, and then the saturation level is another thing that is affecting it. If the funding is enough, perhaps we can actually venture into it. But again, you know, what does it mean? This is a regional specific curve number, regional specific lambda issue already, which means that sooner or later on, it will have regional specific soil number or soil classification. So that is something for me will be considered to be the secondary research after this primary fundamental research to look into it. But to me, it doesn't matter what kind of a soil that you try to classify, the geological formation and the foundation is the one. Those who actually in the construction, if you do the piling, if you pile up and then you take the soil sample, you will see different kind of a geological foundation down there, which is uneven. So classifying the watershed according to the soil type has its own issue as well, because you don't know how thick a certain soil type is at. You only know a general characteristic of it. And if it is a regional specific, my question is it feasible enough to spend that much amount of money just to study the geological formation, foundation, and then to classify the soil type? For one watershed only, it will become expensive. We tried already from the United States of America. Professor Hawkins, he's not doing it anymore because geological formation and the foundations at different state basically is different. And then he suspect the saturation will basically change or tweak the curve number. That's what I need to publish this journal into the mathematics. So for mathematician, they look at the application of a hydrology and the geological formation with the curve number calibration of how the methods of the statistics. So in this case, the key tool is using the inferential statistics to calibrate the model. So my concern is how much money are we going to spend? And at the end, will it become useful information to serve even to the medium term, not to mention long term? Then we can decide how much funding, how much to spend on it. That's my questions I got about the soil type. Thank you for the question anyway.
Sorry, just to curious to know, geological formation meaning what? Meaning what type of information?
Geological formation, if we actually look at it as a get lapis, somewhere down the watershed, how many layer of how thick the soil formation is, we don't know until you really study the study site. Even though let's say according to SES they have a ABCD. Let's say that we already classified in KL Klang area of the of one site that has soil type A and type B and type C. My question is, how thick is type A? That layer of the cat lapis versus the how thick is a soil B, and how thick is a soil C, and whether or not there will be a granite down there mixing somewhere in between, thick layer and everything. So that kind of a thing is non-uniform. It changes from place to place. Even though at one of a construction site, if actually the area is bigger, you have non-uniform, or what we call non-homogeneous layer and the thickness and everything. So to me, are we spending the money and then chasing our own tail?
Understood. Okay. Okay. Okay, thank you. So I'll proceed to the next question. Okay. Also from Mr. Muhammad Hafizi. Okay, his question is HP11 and HP27 dataset is for rural area. How do you relate this data for the urban flash flood?
Okay,
Mr. Muhammad Hafizi.
Okay, thank you for the questions. Urban flash flood, the flash flooding, this journal is actually not using the hydro procedure HP11 and HP27. This one is a separate collected data set for the Gayo Ara area. So this journal does not use the HP hydro procedure 11 and 27. To me, because I try to make a point that is regional specific, and this revised curve number rainfall runoff methodology for the FRGS is actually meant to demonstrate that the power model basically should work and can work. Instead of IA is equal to lambda S as traditional, I'm the first one to propose that anti-log form should be used, because the original graph basically was plotted on the log graph. As you can see, if we actually look backward, why is the anti-log form not used? So instead of an IA equal to lambda S, perhaps in the future we should look into IA is equal to S to the lambda to calibrate the model. So IA is equal to IA is equal to S to the lambda will be the next focus of the field verification study during my consultancy project with a developer in the future then.
Okay. Hopefully that answers the question for Mr. Muhammad Hafizi. There's one more question from him actually, from Mr. Muhammad Hafizi as well. In your Gayo Ara experiment, are you applying the CN for the whole catchment? That's the question.
CN, it's for the collective CN, one number for the whole catchment. What I want to do is I want to find a project site later on, because most of the catchment is non-homogeneous. In future, I want to, if funding is available or data set is available, I don't want to limit myself to one collective CN anymore. So for the Gayo Ara, because I don't have enough of the funding with the students to go with me, let it be other site. If we have at least 20 or 40 of the rainfall runoff of the data set, we should be able to derive the so-called regional CN within the catchment. Minimum, each of the region will require 20 to 40 of the rainfall runoff data set. But again, if we don't get the collective curve number for one of the catchment, now the challenge is, where is the rainfall station? do we have enough of the rainfall station to have enough of the coverage to identify which one is the upper stream, which one is the middle stream, which one is the downstream? If it is possible to launch that kind of a field study experiments, it's possible for me using this methodology to create a dynamic curve number model, linking them together. So you just picture yourself that the if you have enough of the rainfall network, basically covering, let's say like upper region, upper stream, middle stream, and the lower stream of it, we can actually come out with different kind of a regional curve number and then a runoff, and let it pass on from one region to another region, finally coming to the downstream. It's possible to do that. Theoretically, it can be done. I just don't have enough of the data set. I just don't have enough of the rainfall network to cover of one specific catchment in order for me to conduct that kind of the modeling. That's why I've never been able to have a chance to publish something called the calibrated dynamic curve number network modeling. This is something that I can think of on the spot. Dynamic network curve number rainfall runoff model. That will be my future hobby. So please let me know if any of the participants, if you have one of a site that have this kind of the information that allow us to do that, we will be able to do it in Malaysia.
Okay, so if any of the participants are interested, you can email to Dr. Ling that information. Okay, so we'll go to the next question. This is from Mr. Gregory Titus. The question is, the catchment sites which are ungauged or no rainfall data tends to carry out rainfall runoff modeling in generating flow duration curve for that selected site. Can a general model be simulated and be applied to that specific area? If yes, any limitation or allowance of error?
Okay, I know Greg because Greg from Sarawak Energy actually came and visited me in person with several other engineers and is managing R&D managing directors. Greg, there are dangers of doing it when you don't have the network to validate the information. So theoretically, everything that we teach to the hydrology students, like missing data, extrapolations and interpolations, all those kriging methods, all those actually come to the price of guessing. So I think the questions is we will rather ask it the other way around. How critical is the project at the end that you intend to build or construct? If it is very important, if it is very critical, then probably we do not want to take that kind of a risk. It will be best, according to my experience, it will be best for us to just set up our own rainfall, the collection point, because the rain bucket, the tipping bucket, if it can be mounted at a secure location, not to be stolen or to be borrowed or to walk away easily, probably we should plan out our own the rainfall bucket to get that information, and then at the certain location, midstream, we can do a monitoring point. Downstream, we can actually have a water level stations to capture those information. If all those are not available, funding is always limited. It doesn't matter who you talk to. Even US EPA, federal government agency, is the same thing. We have to be creative. Then all must understand that there will be some sort of a room of error that we have to live with. So we just have to look at the map at the end, based on the conversation that you and I and your team have with the UTAR. We need to lay out the GIS map, delineate the watershed correctly, and then look at to see that whether or not we are comfortable with the on-hand available data. If it is engage the area with it, we just have to live with the room of the error that this model may not really work in that particular area, because we are assuming the rainfall pattern is actually consistent in the engaged area. So you could be right or you could be completely wrong. Okay, the famous word, you know, that the Professor Sukiliti Yusuf from the UTM Water Research Alliance always say, "Hujan sini, hujan sana." Okay, your engaged region may not receive that rainfall at all, and build the model. We just have to assume that you receive that the rainfall amount, and therefore contributed to this runoff amount with it. So that could be a huge type 2 error, because you are assuming. Again, just now we also have a discussions about the soil type. You also assuming that the geological ground absorption or the water retention rate is the same. Can you live with that kind of assumption? So perhaps in our design, in our field model, that our limitation, we have to declare that, okay, huge amount of area according to the GIS regions, how many kilometers or how many percent at the which orientation area basically don't have this coverage, the rainfall network, or the data is actually not available. And then we are assuming that the behavior is basically consistent or whatever with it. If that is the case, then the runoff amount should be this much or whatever it is. If we have some of the so-called the flooding records from the area of the engaged area, that will tells you something about it. So we always need to have some information in order for us to do something extra. So if you want to do many extra things with no information at all, and we're just compounding the so-called error, and then the risk basically will creep in.
Okay, so hopefully that answers the question. Is there any more questions from the floor? Okay, you can still add more questions. Just some announcements here. The slides have been uploaded into the handout tab. Feel free to download it. So it's already ready in the handout tab.
They can click on it. You have the full download link to those journals, so you can take a look at it in the appendix area. Some of them has some guided short tutorial. Try to understand it. If not, contact me.
Okay, is there any more questions? Maybe while waiting for another question, maybe from a question from myself. I'm not really a water person, but I understand, Dr. Ling, your research is at the fundamental level stage. In terms of application-wise, and eventually you will go to certain. Of course, they're going through studies and at the government level and so on. Does it go to certain standards, or like MASMA or standards like that?
I wish to be able to collaborate with the USM because on the MASMA, those who know MASMA, the MASMA 227 chapters is actually using the rational methods. Curve number, it's somewhere as an alternate situation with it. If it is possible to not use the rational methods, perhaps we don't have the area of the limitations anymore with it. So I'm also open to that kind of a discussion to see that whether the revised curve number model could be incorporated into the MASMA design at a higher level. Then how much of the revision that we need to revise on the remaining of the MASMA chapters, that one is also remaining as a question. For the government agency level, I think that the DID or the JPS will be the one that I want to serve and share my research outcome with it, because curve number model only have 2 parameters, which is very cheap. If you want to implement to get a quick information out of it, instead of waiting for the rainfall network to be constructed by the MMD or to the or by the GPS or the DID rainfall monitoring network stations, that we can actually have some of the short-term information that we can gather from the site for the watershed and the catchment. I'm working with a developer for more than 2 years already to address the pre and post constructions and the drainage constructions need and their site by using the curve number model. The fundamental, the FRGS, the fundamental research is on the revised curve number, which is the power model. So anything that I talk about before the power model today, up to, is that all there is to help? It actually has been implemented on the developer construction site. Only during the MCO lockdown period, it triggered me to relook at it, and then I saw this log graph, and then I start to submit my FRGS by rederiving the whole methodology over and over again by trying to incorporate and then simplify and calibrate the equation with the power model. So power model is actually quite new. Power model is not even 2 years old, it's a year and a half old. All the data is been tested. The hydro procedures 11 and 27s, the rural data sets, and then you have a Gayo Ara, Kerayong, and then you have a Greece and China. This is actually mixed. Gayo Ara and Kerayong, people would like to see that as the urban site, but if you really want to be correct, non-homogeneous catchment and the data, the watershed basically is huge, is large. I just don't have the funding and opportunity to look at the region within the region or zone. Maybe I should say the zone curve number. If we have a regional specific information on the curve number, it's collective one curve number to describe the rainfall runoff characteristic of the watershed, whether or not we can zone it out. Zone A, B, C, D have different kind of a model, different kind of a curve number, different kind of a lambda, and eventually we link all this zone up to become the curve number network. That is something that I want to experience and very interested to look at it. But again, this requires some of the funding, and this is at the higher level. US EPA, the information that I serve is actually very nearby to the stream because they are working for the preservation, working for the conservation, and working for the pollution detection. So it's always for the short term. And then they pick up my mathematics journal when I derive the methods, and then claim that it's actually return period free. So going back to Gregory questions, whether you're using the IDF, again, great, based on our discussions that your team and I have in the UTAR, when you try to create those kind of a curve, you're using the historical data. So my question is that you believe in climate change or not? So the longer of the historical old data that you use, you're probably setting yourself up that you are not able to cater for the future climate change scenario. If the rainfall pattern change, you may not be able to capture. Just like Professor Hawkins, when I shared with him about the Peninsula Malaysia model, he was shocked to see the recorded storm event up to 230 mm. To him, it's just like, I've never seen it in my life. If it is more than 150 mm, because he used the inches, more than 150 mm is basically start to flood in the US already. That tells you that different region, different zone have different kind of the rainfall runoff the characteristics. So we all need to bear that in mind as well.
Okay, thank you, Dr. Lloyd. We have one more question here from Engineer Abdul Rahman Kadir. The question is, can we relate CN and flooding hazard map as early warning method? That's the question.
Sure, no problem. Because you have to remember that based on the equation that we are studying rainfall runoff, the beauty of it is the Q. The Q part will basically tell you that how much is the runoff depth, or in other words, runoff volume. So the volume for the flood warning and the early warning or the pollution tracing, that's what EPF was interested. Instead of using this equation, they are providing their field recorded data for the past a year and a half in order for me to formulate what is the Q amount for them. So the network that I'm mentioning just now, that if I have a chance to work with the agencies, that we can actually zone it out. We have a zone 1, zone 2, zone 3, zone 4. This is the network. The curve number from each of the zone can be linked together. We can have a dynamic curve number prediction network already. You can see that it's coming from zone A, how much, how fast, to zone B, to zone C, and then to zone D. We all have to pray that if zone D is actually the outlet and the downstream at a time, that how much time that we have before we evacuate or whatever. If it is a pollution source, it has been proven already. US EPA, they want to know that how much of the concentration has been detected in different areas. That's what I'm confident that the zone curve number will work, because US EPA experience from the stream, they have been able to detect the concentration. So for them, they have to quickly pump in the so-called the chemical to neutralize it at the middle stream, or to dilute it before it reach the so-called the monitoring point. So based on the experience that I have with the US EPA, I'm pretty confident that it will work as long as we set it up correctly. And again, the prerequisite is basically the land use, land cover of the whole watershed. If we do this kind of a pilot study or the monitoring, better don't change. Okay, we spend a year and a half, we set up this zone network, they're interconnecting to each other. Suddenly, the nearby upper stream or the middle stream, you have a huge construction development converted into the residential area. That pretty much translates to restarting and then remapping again, because now we have a huge contribution of the so-called the surface runoff or the extra runoff from the daily life, people doing the car wash, pipers, and everything else. Non-revenue water loss actually is a huge issue in Malaysia. All those things will complicate your information when it passes from zone to another zone. So in Malaysia, there's always a challenge as well. You cannot really lock down a watershed or a catchment from by restricting and limit their development. That is a challenge in our country. Yeah.
Okay. Thank you, Dr. Ling Lloyd. Is there any more question? So if there's no questions, so I think we can conclude this talk. So I would like to thank our distinguished speaker today, Engineer AP Dr. Ling Lloyd, for his very useful sharing and also important information on the urban flash flooding and the revised curve number model. Hopefully from his study and his research, we can improve the situation not only in Malaysia, in other places as well. And I would like to also thank you for the participants for attending. Oh, there's one more question from Hafizi.
It's okay.
Okay, I think okay lah. We'll just one last one. After that, we'll because we still have time. So it's okay, Dr. Ling Lloyd? So,
yes.
Okay.
Yes.
Okay, so we'll entertain the last question from Mr. Hafizi. So what is stated in the USDA is CN for the land use, not catchment, which is mixed land use. Please advise. I repeat that again. What is in the USDA is CN for land use, not catchment, which is mixed land use. Please commenting or something, or please advise for Mr. Afizi.
Okay. If I understand the question correctly, yes. That's why for the SES practitioner, they have to select a curve number to start in order to put into your equation. Your S basically have to calculate out. I'm not comfortable with that when we go from the project and go to the site to site. The situation might be different, and the common practice of tweaking the curve number to make it work basically is already reaching the so-called abusing stage. Okay, people plug into the get according the land use and land cover from the guided handbook, and then if it really didn't work, they just adjust it to the point that actually it will work. It becomes not meaningful to me, and then it's non-scientific. Is there a way that we can actually generate the curve number based on the rainfall runoff? The rainfall runoff can be collected from an area. The rainfall runoff can be collected from the entire watershed and catchment, and therefore we can actually collectively produce the curve number for the specific watershed. Which means that even though it's a non-homogeneous best collective curve number to represent the entire watershed and the catchment. Let it be the mixed development, the urban and rural mixed area. We can actually get something out of it, as long as your rainfall runoff data eventually your model has some acceptable prediction accuracy on a runoff that you can live with, you're happy to deal with. Our job is done already. Just now I mentioned about the climate change. The use of the historical data to calibrate the model is actually very dangerous. So please download and then refer to my type 2 error in the Peninsula Malaysia. You can see my comment, because at the end, by using the information, the rural rainfall runoff data set information for BID HP 27, I'm able to separate it into different part of the rainfall runoff prediction model. Recently, I published one more journal, of which I didn't mention or over here, is the so-called the decadal runoff, the analysis, and I managed to correlate it to the Malaysia forest area and then the urbanization population. So if you Google my name with the so-called the decadal forest or deforestation, then you'll be able to find out. I think it just published last week. That one is also based on the DID hydro procedures. I'm under the rebuttal right now to use the power model to reanalyze the decadal forest runoff, the rainfall runoff model again, which might be the interest to the Gregory Titus. Greg basically has my WhatsApp and my email, the account and everything. He can actually continue to pursue that kind of discussions with me as well. I'm also waiting for that journal to finalize so I can have version 1 and version 2, two different way of calibrating this curve number model to benchmark basically for your project grade. So we answer two questions at the same time with it. Back to you, Ayaza.
Okay, thank you very much, Dr. Lloyd. Okay, I think we can conclude the talk today, and thank you everyone for attending the webinar, and hopefully there's a benefit from this discussion and talk. Okay, thank you, and have a good weekend.